142, and that's true. When I teach undergraduates in chemistry, I teach the second semester of general chemistry. How many people have had chemistry? A course in chemistry. Okay. Well, the reason that I choose to teach second semester chemistry is basically we tend to take off right where you're leaving off in high school chemistry. So chemistry 141 is really a review of high school chemistry. Probably you're going to go into a little more depth than you would in your high school classes. How many people have had AP Chem? Yeah, so it's about that level, so 141. 142 is really a little more of general chemistry theory. We get into kinetics, mechanisms. The math tends to be a little more involved in 142. It's just the course that I enjoy teaching more. I like kinetics and mechanisms and thermodynamics, and that's what I teach. So what I try to do when I come and meet with you guys is really give you a preview of what you're going to see in your classes, in your intro classes. So you've had somebody from bio?
Mm-hmm.
Math?
Yes.
Okay, and I'm going to cover chemistry. So typically what I would do on the first, I'm going to do what I would do on the first day of the spring semester when I teach this course. And that's basically to introduce myself. And typically, this is from spring 2012. Typically, when I teach the class, we'll have between 80 and 110 students, so it's a very large class. So I teach the class, and then I typically have a PhD graduate student assistant that helps me with office hours and helps meet with the students when they, when they're looking for help outside the classroom. So I want to tell you a little bit about myself. Got my undergraduate degree at the Pennsylvania State University, Barron College. I got my PhD in chemistry from the University of Kansas, Rock Chalk Jayhawk, go KU. I'm a huge college basketball fan. Love the Jayhawks. After that, I did a postdoctoral research stint at the California Institute of Technology in Pasadena, California, before coming to Emory. So that's kind of my trajectory getting here. Does anyone know what this is? It's kind of hard to see.
Kiwi.
It's a kiwi. That's right, it's a kiwi bird. Well, the reason, where are they found? Oh wait, I heard it. New Zealand. That's right. They're found in New Zealand. The only reason I show this is because I married someone from New Zealand, and most people think that kiwi's from Australia, but it's found in New Zealand. It's kind of slow and flightless, but I like it. The other thing that I'll tell you about myself is just that we have a couple of rescue dogs. They're Catahoula leopard dogs. They're big hounds, and I love them very much. So we got both of our dogs after Hurricane Katrina. That's something I have a lot of fun doing, playing with in my spare time. So that's a little bit about me. So I'm going to jump right into Chemistry 142 and tell you a little bit about the course. Do you have the syllabus in your packets? Maybe you don't. If you don't have it, don't worry about it. We can go over it.
It's under activities, guys.
It's under activities. Because if you have the syllabus in front of you, that'll help us with this exercise. Typically, I would pass this out on the first day. The other thing I want to tell you is all the material you're going to get in any of your courses, the material you get is going to be posted online, okay? You're going to have a course website that you can log on to. You can get all the handouts, you can get all the study guides. You'll have access to everything. If it is a large class and the professor's using PowerPoint slides, PDF copies of those PowerPoint slides are going to be posted there as well. Notes about the course, office hours, review sessions, all of that will be posted to that website. So the syllabus for any course is really your course roadmap. Provides you with essential information about course content and how to succeed. It's going to have course information, content, important dates, including things like exams. How many of you have a good calendar system right now? Calendar that you refer to every day. Electronic, maybe on your phone. If you don't have one, get one now. And what you want to do is on that first day, go home. You're going to see the exam dates, get them in your calendar, start planning, review session. You want to have a good personal time management system. The course syllabus should also talk to you a little bit about evaluation. What do I mean by that? How are you going to be evaluated in the course? What matters? What counts? What contributes to your grade? Course particulars. technology and assignments, how to be successful, and resources available to help you outside the course. So these are all things that you should look for in a course syllabus. So I want to go through our syllabus and tell you a little bit about what I feel my role is when I'm teaching freshmen introductory chemistry, is really to relate and describe the relevant chemical concepts to you, to everyone in the course, and to be precise and diligent in teaching, assignments, grading, and exams, so that you leave Chemistry 142 with an appropriate knowledge base. So many courses require 142 as a prerequisite, right? Have you been looking at course catalogs from Emory or Oxford? So many classes, you have to have 141 and 142. I have to do my job to get you that information so that you can succeed in those 200 level courses, so that you can go into biology, biochemistry, and do well. The concepts you learn in this course are essential. So I want to talk a little bit about your role whenever you take, and so I'm specifying this presentation like it's 142, but it's really your role in any class, is to be actively engaged in the learning process and environment. It's not good enough just to come to class. The courses are going to move at a considerable clip. You've got to come, you've got to be engaged, you've got to participate. You must keep up with assignments and reading. I'm going to talk to you a little bit about the pace of the course typically, but you've got to, excuse me, you've got to keep up. Don't fall behind. Really, really important. I can't stress this enough. One of the challenges I face in teaching second semester is I get students who make it through their first semester relying on memorization, right? They don't learn the concepts. Instead, they learn to memorize the material. It will not work in this course. You can make it through the first semester okay. People usually don't light it up relying on memorization, but they can get through maybe with a B. You'll crash and burn in this course if you try to rely on memorization. You have to understand the concept. You have to be able to integrate multiple concepts together. Don't memorize. It is not a recipe for success. You've really got to understand. Lastly, use the resources available to you. So typically I would go through and do a little survey. Now, in that syllabus that you have in front of you, I want to, before we jump into the course material, I want to talk a little bit about the content and the pace of the course. So you see, this is the chemistry, this is the textbook that we would typically use. You can see the course content. I give you the textbook and I give you the chapters. Chapters 11, 12, 13, 14, 15, 16, and 17, and 18. So we're covering a lot of chapters. For many people in the class, the material is going to be new, right? If you don't do it in that first semester of AP, it may be new material. This course, when I teach it, it's only taught 2 days a week, Tuesday and Thursday. So we cover about a chapter every 2.5 days. So every 2.5 lectures, we're going to be through a chapter. With every chapter, I'm going to assign between 30 and 40 homework assignments from the back of the book, and you're going to have to do the ALEX assignments. You're all familiar with ALEX. You're using it right now. ALEX, traditionally what I tell students is do the ALEX stuff first, then go to the homework out of the back of the book, because the ALEX stuff is going to be easier. Okay? The stuff at the back of the book problems are really going to challenge you. So why am I telling you this? Why am I telling you the pace that we're going to move and the amount of homework? I'm telling you that because really, you need to dedicate time to these courses. You have to spend the time doing homework, doing the ALEX. Do it early, practice early, and practice often, okay? You cannot wait until the week before an exam to start preparing. That brings me to the next part of the syllabus, important dates. We've got the first day of class, January 19th. This was a year ago. Our first exam is mid-February. The second exam is close to mid-March. And we have a third exam mid-April, and then the final. Right? So that's basically it. Those are your chances to be evaluated in the course. Final exam is typically worth 30% of your overall grade. 3 in-class exams worth 40%. ALEX, the 2 different modes, those count for 10% total. And there's a laboratory component also. So in addition to basically the 2.5 hours a week you spend with me in lecture, you're also going to be spending 3 hours in lab. Now what I tell students is for every hour you spend in lecture, you should be spending 3 hours outside of class on material. So if you're in a lecture for roughly 3 hours a week, you need to be spending 9 hours outside mastering the material. And the students who do that do well. The students who put the time in and start early will do well. I've never had a student put the time in and invest the energy that hasn't done exceptionally well in the class. Where people get into trouble is when people try to wait to master the material the last week. So I'm just telling you, plan early, plan for success, put the time in, you'll do well. Anything else? I guess the only other thing I want to point out on the syllabus is if you look at the first page of the syllabus where I talk about office hours. So office hours, that's a time that I'm always going to be in my office. You can come by and see me, right? Stop by with your questions from Alex, from the homework, whatever. Stop by, I'm going to be there. Omar, my teaching assistant, he also has office hours. He's fantastic. Others, it says by appointment only. So I want to talk to you a little bit about this. By appointment only. You're going to see this on everybody's syllabus. So if you can't make my office hours, and there's a good chance you're not going to be able to make all of your professor's office hours, right? They typically only have a couple hours free each week. You're going to be involved in extracurriculars. You'll have other classes. These lab classes take up 3 hours. Come on, chances are they're going to overlap, right? So you'll see that most people say by appointment only. If you can't make a faculty member's office hours, reach out to them, email them, set up a time that works for your schedule. They'll make time to work with you. The other thing I wanted to say about my particular rules in my classroom is if you look, there's an asterisk by the by appointment only. And then if you look down to the footnote on the very bottom of the page, office hours individual meetings will not be offered the day before an exam. I learned this a long time ago. If you're waiting until 24 hours before your exam to come and see me, coming to see me is not going to help. Because if you've waited that long to make an appointment, there's nothing I can do or Omar can do to help. So basically what I have a policy on the books, I won't meet with any students the day before an exam. If they've waited that long, I can't physically help them. Why am I doing this? Because I'm a meanie. I know that's what you're thinking. Not at all. I want more than anything for people to be successful. But I just want people to reach out early so they have time to master the material. That's all I'm going to say. It takes time, and it'll sneak up on you. I've seen this happen to students. They'll be doing well. They'll be doing well. Kind of seen some of this in high school before. They're doing well. They're doing well. We get into thermo, and they hit a wall, right? And they let the work go. They don't keep up with Alex. They don't keep up with the homework, and then the third exam is a crash and burn. So stay on top of the material. Stay engaged. Stay on the homework. So I told you we'll typically cover a chapter every 2 to 2.5 lectures. What I wanted to do today with a little bit of time is just go through one section of one chapter. So if we start with chapter 11, and that's traditionally where we start in 142, if I start with one chapter, chapter 11 has 8 different sections in it. We would probably do in a normal class period, between 4 and 5. I just want to do one section with you today, so we can give time for questions. So mixtures versus solutions. So this whole chapter is really about the difference between a mixture and a solution. A mixture has 2 defining characteristics. Every mixture, its composition is variable, and it retains some of the properties of its individual components. So some of the individual things that make up the mixture contribute to the properties of it. A solution is a homogeneous mixture, okay? The components of a mixture are uniformly intermingled, no boundaries separating its components, it's all one phase. So whereas a solution is a type of a mixture, it's a special type of mixture where it's homogeneous, okay? So things like concrete would be a heterogeneous mixture, right? You've got sand, you've got pebbles, you've got all that stuff. You can see the pebbles in the concrete. Solutions, everything's homogeneous, it's all one phase. You can't see defining characteristics. Solutions can exist as gases, they can exist as liquids, or they can exist as solids. So the concrete example. So let's look at some different type of solutions. Okay, and remember, solutions are homogeneous mixtures, right? We have air, natural gas. These are examples of gas solutions. And typically in a solution, we're going to define a solution, a state of the solution, state of the solute, that's the thing that's going to be dissolved, and state of the solvent, that's the thing that does the dissolving. So in something like air and natural gas, the solution is gas, the solvent is gas, the solute is gas, and the solvent is gas. If we take something like vodka, right, alcoholic beverage, it basically consists of mainly water and ethanol. The state of the solution is liquid, state of the solute is liquid, and state of the solvent is also liquid. You can have solid solutions. Brass. Brass is a mixture of copper and zinc. Carbonated water. Carbonated water, or in soda, we're basically dissolving, right, gas molecules into a liquid. You know, that's why if you leave your bottle of Coke in the sun, and then when all the gas tries to escape the solution. But that's also an example of a mixture. So, because solutions have variable compositions, the amount of substances in a solution has to be specified. So where we're going in this whole first part of chapter 11 is we got to teach you. You've got to become really comfortable with describing relative amounts of solutes and solvents in mixtures. Does that make sense? So here's the thing about chemistry. Chemistry relies a lot on your ability to do math. On every exam that I give, at least 60% of it is going to be manipulation of equations in mathematics. About 40% is going to be basic concepts, understanding, explaining, diagramming, drawing, things like that. But to do well in this course, you're going to have to be comfortable manipulating numbers. So if we want to describe a solution's composition, there's a number of different ways we can do it. We can talk about molarity. How many people have heard of molarity? We've all used molarity? Good. Mass percent, mass weight percent, we use those. Some people have used those. Mole fraction, where we actually talk about the moles. And then molality. Our biologist friends love molality. Molality. I don't use it much in my lab, but I know the biologists like it. So what you can see, what I want you to see from all of this is it's really just learning how to manipulate values to describe a solution or a mixture. So let's go ahead and take an example. We've got molarity. And this is what we do in the class. We'll spend at least 20 to 30 minutes each class just going through sample problems so that you can get comfortable before I send you out to do all the homework. So let's try a little exercise. So you have 8 grams of H3PO4 in 100 mils of solution. Calculate the concentration in molarity. And typically what I do is I'd say you've got about 60 seconds to go ahead, whip out some scrap paper. Go ahead, you can do it, we're going to do it together. Right, you've got the equation up there. Oh, but what you don't have is the formula weight.
Yeah.
Formula weight of H3PO4 is going to be 98. Hold on. Sorry, yeah, 97.99 grams per mole. 97.99 grams of H3PO4 per mole. That's its molecular weight. So you've got 8 grams. And I'm assuming everybody has some sort of cellular device that they can do calculations on. I kept these easy. You guys have your laptop? got it. I know you guys weren't expecting this. I kind of sprung it on you. But you're having fun. Look at this. You're having fun. Are you checking your answers? That's a good idea. I think it's a good idea. Check your answers. Did you get the same answer? Did anyone get it? I'm gonna wait a couple more seconds for other, because I see people are really close. I see numbers. Yeah, well, in the class you would have to do scientific interpretation, but I'm fine with this. This is good. Okay, it's fine to start. See? So you're getting a refresher. What do you get? It's in 100 mils. So 100 mils is 0.1 liters. So 100 milliliters, sorry. Sorry, I saw a couple of people. That's okay. That's the other thing you have to get really quick at is just doing those conversions kind of in your head because we'll use them all the time. But the nice thing is we'll only use like liters and milliliters. We won't go to ounces. That's really confusing. Okay, how many people now have answers they're happy with? 1, 2. I like it. Yeah. Well done. Okay, what do you get?
0.816.
0.816? I'm seeing a lot of head nods. You're close though. No, you want help. Okay. See, now typically in the classroom, even though there are a lot of students, we'd be walking around. Yeah, that's where it went wrong. So if you have 8 grams, you would basically like 8 divided by the 97, and then everything else was right. Oh no, we lost. Okay, so basically what we would do at this point is we would just keep doing a few. We would do a handful of practice problems, and I'm not going to make you do this because I want you guys to have time, but typically what we'd do is we'd do 5 or 6 practice problems in rapid succession. We'd do some clicker problems where you could answer and get points, and then we'd move on to the next section. Because what's key to almost all of this is once you have the basic mathematical language, once you can do these basic transformations, describing mixtures and solutions, well, describing solutions by their mathematical designations, you'll be able to understand the concepts more easily. So typically we start each chapter with an intro to the basic math, the basic manipulations, we practice them, and then we go in more in depth. So, and the other thing is, you'll get really used to it. Depending on who your instructor is, you'll get used to doing a lot of in-class problem-based learning. So we would do a sample of all of these. And honestly, we'd get this done in about 10 minutes in class. Sorry. Okay, And then what we would do is after we do that basic introductory material, we'd move on to the next section. And we would go into the energies of solution formation. And this is where we actually start talking about things like enthalpy, the energy required to make a solution. Have you ever dissolved anything and had it get cold, the container get cold? Like dissolve salt or something into water? Yeah, there's energies associated with the solution process. So in the first part of the chapter, we would cover just the basic descriptors. How do you make solutions? What are the components? The second part, we're going to talk about intermolecular forces. We're going to talk about enthalpies of formation. We're actually going to look at some movies that show you how dissolution works on a molecular scale. And this would be the second part of the second of those 8 sections of the chapter. And what you'll see is now we're doing introductory material, but each one of these start having delta H's associated with them. So you know what's coming down the line is we're going to start doing math. We're going to start looking at energy associated with these processes. So one of the reasons Drew asked me to come each year and talk to you is to kind of stress the importance of the math and the mathematical concepts. Even though it's not a math class, it's really important for your studies in chemistry to be able to do basic manipulations and things like that. So anyway, that's my brief intro to what it would be like. Basically walking in second semester of your freshman year, that's pretty much what your course is going to be like, only we would go for an hour and 15 minutes. And I wanted to give you time to talk to me about questions, concerns, advisors, whatever. I also advise undergraduates, chemistry majors.
Yeah.
I work with them. Go ahead.
Do you begin thermal chemistry?
Mm-hmm. Yep. Thermo, we get into chapters 16, 17, I believe. Yep. We'll do thermodynamics. Yeah, that's a big part of it. Then we go from thermodynamics into electrochemistry, which is kind of jarring. But I'm going to go over here.
Do y'all use the same book in the first and second semester?
Yes.
And all professors use the
Yes.
same book? Okay.
Yes. So you can go wherever, and it's going to be the same.
Will we have a review of molecular geometry?
In the second semester, no, because I think that's covered. Well, okay. So to answer your question, we review it second semester inadvertently because in the second semester we start talking about things like Lewis acids and bases. And to understand Lewis acids and bases, you have to kind of understand molecular geometries and things like that. So you have to know it, but when we introduce the concept, we do a quick review. I always stop and say, hey, everybody, remember you learned this first semester. This is how you figure out geometries and load pairs, things like that.
Okay, so when you say you give out like 30 to 40 assignments,
Homework problems, yeah.
homework, okay, that doesn't count in our, that wouldn't go in any one of these categories?
Nope, if you don't do it, the only way I know is based on your exam performance.
Okay.
And I'm not saying that to be mean. Oh, but you know what though? The other thing is I always know who's working on the homework because I put 3 or 4 problems that take me forever to solve. Because I'm like, oh, how do I do this? And typically the students who end up in my office are the ones doing the homework because they'll get stuck on the same one. So it's not me, well, kind of. You don't get any points for it, but I know who's doing the homework because the people who get hung up on the difficult problems come in. Or they form study groups. I know a lot because the classes tend to be a little bit larger, bigger enrollments. Students will live in the same dormitories with each other and they'll do study groups. And I know I've been at home, I'm not kidding, at 9 o'clock at night and I always have my iPhone with me and I will get an email from students and they'll be like, Dr. MacBeth, we're stuck on 88, part 3, how do you do it? Just tell us how to set up the problem and it's me and Aisha and Sam and Max, so just tell us how to start, So I know people are working on it, right? Because I'll get a group email saying, tell us how to start the thing. And so I'll help them. But the reason it's important for you to do the problems is that, I tell people chemistry is like a sport. You got to practice it to be good, right? You have to get out there on the track. You have to put the time in, running sprints to get your times down. Chemistry is the same way. Sometimes people can do it, but they're not practiced enough to be able to do the material on the exam in the time allotted. Does that make sense? Like they're just not fast enough. So it's a little bit like training for a sport. You just need to, just practice a little bit every day. One of the things I tell students that, because sometimes students will say, I'm just going to go back. Sometimes students will say the pace is overwhelming, because it just seems like we're going so fast. But what I'll tell students is I'll be like, look, in chapter 11 there are 8 sections. First lecture, maybe we get through chapter 11.4. The thing is, all the homework assignments that I'm going to pass out to you or ask you to do in the back of the book, they're grouped by section. So, 30 to 40 problems seems like a lot, but guess how many of those questions are going to be from 11.1? Not that many. So if you can just concentrate on that little part and break the chapter up, it becomes much more manageable. You know what I mean? You take a 30-page chapter, break it up by section, you're like, oh, well, that's not so bad, right? I only have 4 or 5 pages. And then if you look at the homework just assigned with that section, it's completely manageable. So some of it's up here. Like, you've got to convince yourself it's doable. And trust me, when I look at all that, I'm like, oh, I don't want to teach this. I don't want to assign these problems. Then I'm like, let's break it up. Let's just do it one section at a time. And if you can get your head wrapped around, around this concept of divide and conquer, forget that. You can do it. And it's not so bad. Then you have to change your thinking. It's like 5 problems per section. Not bad, right? But that's why it's important for you to stay on top of it.